Hello, I'm Dr. Ian McCullough, and today we're going to be talking about the statistical design of experiments. And statistical design of experiments is all about the strategy that you take when you're doing an experiment. Okay, so first of all, let's define what an experiment is. So an experiment is a test, or it's a series of tests in which you're going to make purposeful changes to some sort of input variables, of some sort of process, and then you're going to observe the resulting changes on the output variables. Right? So that's what an experiment is. So I'm going to draw a little diagram of that. And so let's say that I have a process here. Okay, and in the process, I'm going to have some set of inputs. So we'll have inputs. And on the other end here, we're going to have some output. And I might call this output Y. And then there's going to be some set of controllable factors that are going to be affecting this, right? You might have x1, x2, all the way up to, let's say, x. I'll use subscript p there for factors. And then you're going to have a set of uncontrollable factors, right? Same kind of thing here. These are uncontrollable factors. We sometimes call this noise variables. And so we'll use z1, z2, zg factors. Okay? So we have a process. We have input variables, output variables. We have a bunch of factors. So I'm going to give you an example. So I like to run, right? I like to keep in shape. And so what we might think of as the output variable, when I do this input of running, we might think of the output variable as time. Well, what are some of the other variables that I could use? Well, it could be like I could wear different shoes. I could wear a jacket when I run. I could listen to music. I could be hydrated. What about the food, the diet that I have chosen? Am I running on a pavement or trail? Is it the morning or the afternoon? Morning or afternoon? What's the temperature? Is it raining? Wind? And of course, I mean, you could just continue to list a bunch of other different factors. So if I want to understand how these variables are going to affect the time, and maybe I want to optimize my time, I want to run as fast as I can, well, there's some strategies that we have in experimentation. So one strategy, right, is I could set factors, right? I could, take a set of factors, and I could change one multiple times, okay, and then I could hold the others constant. And that approach is called the best guess approach. What does that look like? Well, what it's going to look like is I'm going to say, hey, I'm going to make shoes be my factor that I'm going to choose. I'm going to keep all the other things constant. I'm going to listen to the same music, wear the same jacket, drink the same amount of water, eat the same food. I'm going to run on the same trail. I'm going to run at the same time of day. Now, when you get to these temperature, rain, and wind, those become these uncontrollable factors, so I might have a little bit of an issue with being able to analyze those, but I just hope that they're all kind of somewhat consistent, or I look for the times when they're consistent, right? And so that's how I'm going to be changing one set of factors at a time, right? Which factor is going to be significant. The next one is a little bit different. I'm going to baseline. So I might run a few times with everything consistent or the same, and then I'm going to alter one factor at a time. That's the name of the approach. So instead of guessing which factor to change and then testing it out, what I'm going to do is I'm going to systematically have a baseline, and I'll try different shoes. Then I'll go back to the same shoes, and I'll try a different jacket. Then I'll go back to the same jacket. Then I'll systematically do one factor at a time to see how each of those things are going to be changing. Now, it's a little bit more systematic than this approach. However, it's going to be a lot more time consuming if I have to change every factor, then I have to verify it. The other problem that the one factor at a time in the best guess approach does is it fails to consider interactions, right? Fails to consider interactions. Well, what is an interaction, right? Well, if you have multiple factors, sometimes one of the factors can behave differently in the presence of another factor. I'm going to use a slightly different example, and I might look at, have you ever seen a dimmer switch, where if you increase the dimmer switch, the light gets gradually bigger, like brighter, and as you decrease the dimmer switch, it gets gradually lower. So it might look something like this. If I have the dimmer switch setting, right? Well, we'll just call this X for now, right? But I have the dimmer switch setting, and then this would be the brightness of the light. So brightness. Okay, that as I take this dimmer switch and I go from here up to here, it gets brighter, right? So that's what we would expect. But, so this would be the dimmer switch. But what if the circuit breaker is turned off, right? What if the circuit breaker is turned off? Then as I increase the dimmer switch, what's going to happen to the brightness in the room? It's just going to stay flat, and it's not going to, nothing's going to happen. So this would be the condition when the circuit breaker is off, and this would be the condition when the circuit breaker is on. So the effect of one variable behaves differently based on the setting of the other. So if I have the circuit breaker off and I'm doing an experiment, I can change the dimmer switch all day long and nothing's getting brighter in the room. However, if the circuit breaker is on and I change that dimmer switch, then it does have an effect. And that's called an interaction effect, right? So when we look at these variables, there very well might be an interaction between food and hydration, for example, right? Depending on how hydrated you are, the food is going to have more or less of an impact. Or maybe if you have no energy because you haven't had the right food and you're not hydrated, it doesn't matter how energizing the music is, it's not going to have an impact on you because you have no energy. But if you do have the energy and you're just not motivated, you're not going to run fast either, so you need both, right? So those are interactions. So when we have, when we're trying to model these interactions, what we want to do is we want to conduct a factorial experiment. Okay, and we're going to spend a bunch of time here talking about what a factorial experiment is and how we conduct it, and how we conduct it efficiently. So our ultimate goal is I want to get the most information with the minimal amount of experience or experiments. So I'll just highlight that. Most information with minimum experiments. And when I say with minimum experiments, it's not because I'm lazy, although maybe I am lazy. It's really about cost. So I think the first real project that I did with statistical design of experiments was dealing with armor penetration. So at the Army Research Lab, they would take a projectile and they would shoot it at an armor plate that they would have made to, try to withstand, bullets better. And so then they would shoot it at the plate, and then they would have to shoot it at increasingly higher and higher velocities so they could estimate at what velocity would the bullet penetrate the armor. And so as they're going through these experiments, each experiment costs close to $250,000 to run. So, 4 experiments, that's $1 million test. And so when they're trying to design the experiments to be few, it is not because of time as much as it is because of the cost of running the experiment. Another project I did was dealing with developing explosive detonators. So for explosive detonators, it uses a chemical called lead azide, and it's a key ingredient in explosive detonators. The old process that they used to use in the 60s and 70s was environmentally unfriendly, and so they had stopped doing it. They had stockpiled it, and as we had wars in Iraq and Afghanistan, we needed more, and the stockpile was being depleted. They literally could not find anybody that had been developing the process. This was in probably the early 2000s. They couldn't find anybody that had been around in the 60s and 70s making the process. I think they had all died of cancer or something really horrible like that. So they had designed a more environmentally friendly process, but they couldn't get it to meet the same standards that they needed, right? So by meeting standards, what do I mean? I mean, you need the explosive to blow up when it's supposed to and not before, right? So there's kind of a sweet spot there. And there was a number of tests. There were about a dozen different tests that they would have to do. That would take a week to perform all of the tests on a batch. So at the rate they were going, they were estimating that it would take about 10 years to go through all of the different combinations of factors with some sort of systematic baseline and then altering one factor at a time. And chemical processes tend to have a lot of interactions, and so they were concerned they wouldn't be able to address that. So I was able to design a statistical design of experiments, and we were able to, within 4 months, actually find what the optimal solution was. And what it was is one of the mixers that they were using was not capable, so they had to redesign the mixer, but we were able to demonstrate what the space of feasible solutions were within about 4 months. And so there's one of my earliest papers was published on that. So in more modern times, right, nowadays I use this in the study of neuroscience, neuroscience of influence and persuasion. And so when I'm in the Middle East or someplace and I'm recruiting subjects, there's high costs associated with the facility rental, with the time it takes to run people through the neural imaging machine. And so the more efficient I can be in the way I design my experiments, the lower I can drive down costs.